Kyle, do you want to be on camera? Hi. Ready? Okay. So here we are in the second kind of review session for Engineering 20 for my online Introduction to Circuits course. City College of San Francisco, open and accredited. Okay. So I'm going to make sure that we all are on the on the same page with first order circuits. So I'm going to go through those and do an example problem, and then I'll go over second order circuits and kind of get you started on that road. But it's really important to know the first order circuits before going on to second order circuits. So here I've got two first order circuits, and I claim that these are really the only two first order circuits that exist in the whole world. Do you agree with that? I know we have one student here, he doesn't want to be named, but he's nodding. So, and the reason is because no matter what kind of circuit you have, if it's a first order circuit, you're either going to have one, because first order means one for energy storage element. So you're either going to have a capacitor or an inductor. And what you need to do is, from the perspective of that energy storage element, you look at the rest of the circuit, and remember we learned that you can always reduce it to a Norton equivalent. So here's the Norton equivalent. Well, always. Has to be a linear circuit, but in general you can reduce it to this Norton equivalent, which you have here, or actually this is a Thevenin equivalent with the voltage source in series with the resistor, or by a source transformation get the Norton equivalent, which is a current source in parallel with the resistor. So really this is it. You can always force your first order circuit to look like one of these. So you're going to have a capacitor with some value C. You're going to have a resistor. Now remember, this is the Thevenin resistance. I didn't put the subscript here just because things are going to get complicated enough. So you just have to remember that this is the Thevenin resistance because we've reduced the circuit to the Thevenin equivalent circuit. And here too, this is the Thevenin resistance. So here are the circuits. What we want to do is come up with an equation that defines it. Now, for a first order circuit, that's going to be a first order differential equation. If we had a second order circuit, it would be a second order differential equation. Third order circuits, you'd have a third order differential equation. So this is a first order circuit. I skipped some of the work here, but basically if you just did Kirchhoff's current law around here and did a little bit of work, that's why I'm showing it with the dot, dot, dot. It's very simple mathematical work that I don't want to waste time with here. You can get this differential equation. And the differential equation comes from the idea that the voltage, remember for a capacitor, no, the current through a capacitor is equal to C dV dt. And we know that, oh God. Okay, Kyle, you've got to help me here, because I want to say that I haven't done this lecture in a year. Okay, it's this way. The current through a capacitor is C dV dt. The voltage across an inductor is L di dt. Okay, so you've got to use these in order to get these differential equations, but again, I know that you can do it on your own in less than 5 minutes, and you get, for this circuit, you would get this first order differential equation. For this circuit, you would get this first order differential equation. And for this one, you wouldn't use Kirchhoff's voltage law, you would use Kirchhoff's current law, and you would just do it for this node right here. So we have these two differential equations for the only two first order circuits that exist in the world, right? Because we can always get our first order circuit to look like one of these. What do you notice about these two equations? They look alike, really. Here we're talking about a voltage, the voltage across the capacitor. Here we're looking at the current through the inductor. But if we just call that variable x, because that's the variable that we're interested in, right? The voltage as a function of time or the current as a function of time. Let's just call it x. So look, then we've got dx dt plus x over, and look, these are just constants, right? RC is a constant in this circuit, right? It's just the Thevenin resistance times the capacitance. L over R is just some constant in this circuit. It's the whatever that value of the inductor is divided by the Thevenin resistance. They're both just constants. Let's give it a name. Let's call it tau. Now, it actually is a significant constant. There's actually a name for it. It's called the time constant of the circuit, and there's a reason for that, which I'm not going to get into now. For now, all I have to just say, it's a constant. So, and then you notice that we've got, on this side of the equation, whatever the voltage source is, and you know, remember, it's not necessarily constant. It could be a function of time, so I'm emphasizing that here, divided by that same constant tau. Here, we've got whatever the current source is, and it could be a function of time. It isn't necessarily constant, although I will acknowledge up until this part of the course, pretty much all of our sources have been constant sources. But I want to get you ready for the time when that's not going to be true. So it isn't necessarily constant. It could be a function of time divided by a constant. So I hope you'll agree that this equation here is a first-order differential equation that describes any first-order circuit. If it's this one, the X refers to the voltage across the capacitor. If it's this one, it refers to the current across the inductor. Tau for this circuit is RC. For this circuit, it's L over R. And then this function here, of course, has to do with the voltage source or the current source. In this case, you're dividing them both by the tau of their own circuits. So here's our first-order differential equation that we have to solve. All right, this isn't a course in differential equations, and I know it's not even a prerequisite for this course. But so I don't expect you to be able to solve differential equations yet. But the first-order differential equation is actually not a hard equation to solve. And again, I'm going to skip the math, and I indicate that by these 3 dots. It was in my notes. It was in the book. I'm not all that concerned to watch you, or I'm not going to test you solving a differential equation. But I do want you to go through it because it's important to know how to do. But here it is. This is the solution to this differential equation. And notice that when you have differential equations, the solution you're looking for is a function of time. It's not just a value of x here. X is a function. So here's the solution. Notice that there's 2 parts of the solution, which is always the case with differential equations. Okay, and they have names. And this one is called the forced response, or sometimes called the long-term solution. This is the transient response. You can call it the short-term solution. If you look at this carefully, as t goes to infinity, right, as time goes on, what happens to that term? It goes to 0. So that's why we call it the transient response, is because that term drops out after a long time, and this is what you're left with. And so that's why we call this the forced part of the solution. So the only mysterious thing here might be tau and y of t. Well, as we said, tau for this circuit was just this constant RC. For the circuit with the inductor, it's L over R. So whatever circuit you have, now you know what tau is for your particular circuit. The forcing function, y of t, comes from the voltage source in this case or the current source in this case. And I told you that those might be functions of time. They're not going to necessarily be constant. So whatever those functions are, that's what you plug in here. And then you just have to know how to integrate, which of course I know you all know how to integrate because you've taken calculus. And so you integrate it, and you've got your solution. For the special case of this being a constant, for your, which is really what we've been dealing with most of the semester, that these are constant sources, the solution becomes actually much simpler. It just looks like this. Okay, so if y of t is just some constant, and I'm just calling the constant m, then, I mean, you can do the math here. It's really quite simple. And you just substitute it in, and you get this. So this is only for the case if your forcing function is a constant. You may ask where this term came from, this x0. I got this by applying what we call the boundary condition. You've usually called it the initial conditions. And it's at t equals 0, I'm saying the value of my function, I'm just calling it x0 or x naught. So that's where this came in, and that's why the k disappeared, is because I actually applied that initial condition. So again, I am skipping some math steps. I'll show you that with 3 dots. But they're very easy steps. I don't want to take the time to do it here. That's what you're going to be using when you have a constant forcing function. If you don't have a constant forcing function, then you're forced to use this more general equation. Okay, so with that background, let's solve an actual problem.